So welcome to Technosciences in Robotics Seminar Series. It's my pleasure to welcome our own faculty member, Mr. Dave Aiken. He's a professor in Aerospace Department and also Director of Space Systems Lab. He is considered one of the pioneers in the field of space robotics, and he is one of the faculty members who started robotics research at College Park. So it's pleasure to welcome him here.
Thank you, SK. What he actually just said is, I'm really, really old. I appreciate the opportunity to come by and talk to you about basically how we keep ourselves busy in the Space Systems Laboratory. If you think about working in space, what you need to effectively work in space, particularly with humans, there's no question that robots are part of space. For all those vast volumes of space we cannot currently get humans to. But even where you do have humans, you're going to really augment their capabilities by providing robotic assistance in various forms. And you can see in this image by John Frazanito and Associates, you have sort of classic astronauts in spacesuits doing extravehicular activity, or EVA. You have robots that are out to assist them. You have workstations for short-sleeve astronauts that are sort of combinations of humans and robots together. And one of the basic themes that we're going to be hitting on time and again is humans and robots working together in space. And that's true not only whether you're talking about it in microgravity or whether you're on the surface of the moon or on the surface of Mars. You're going to see robots on a lot of different scales working directly together with astronauts to keep them safe, to make them productive, and to try to get as much scientific return out of these very large investments as we possibly can. The Space Systems Lab has been in existence for about 35 years. That's kind of scary. I never thought of that before. We started off at MIT and moved to the University of Maryland in 1990. Sort of the crown and the jewel is the neutral buoyancy facility, a couple hundred yards that way. 50-foot diameter, 25-foot deep water tank that we use to simulate microgravity. We're the only university in the world that has neutral buoyancy facility. So I'd like to point that out as many times as I can. The SSL does work in sort of 5 different areas. Human systems, this is primarily human spaceflight, humans in the space environment, dexterous robotics, flight programs, systems design, and human-robot interaction. I'm really going to talk about 3 of these today, primarily dexterous robots and human-robot interaction, and some recent developments in flight programs with our robotic systems. If you look back in time on things that we've done, these are some examples of work that date back a number of years. Robots doing structural assembly, formation flying, multiple robots, a big positioning crane with a robot as a dexterous front end, cooperating robots. This is a free flyer monitoring this dexterous robot and placing a set of foot restraints where a person in the spacesuit is going to come and return a whole space telescope later on. One of the things I like to point out is the name of the laboratory is not Space Robot Lab, it's a Space Systems Lab. You know, I am a professor of aerospace design. I tend to focus on integrated systems development and testing in as realistic an environment as we can. So we really try to bring together systems that evaluate how well they work in the best environment we can to simulate the environment that we're going to be working in. More recent robotics projects in the lab, and I'll be talking about most of these in more detail later, not only satellite servicing robotics, advanced lightweight technology, self-configuring robots, free flyers, and some work we're doing now in deep submergence robots for the undersea community. Probably the simplest system in our lab is SCAMP, which is Space Camera and Mobility Platform. It's basically a free-flying camera platform with cameras, surprisingly enough. As in all of our free-flying hardware, we go to a great deal of effort to make sure the center of mass is coincident with the center of buoyancy, So it has no preferred orientation. We're not building submarines, we're building spacecraft. We want them to behave like spacecraft. These SCAMP units, we have 2 of them, so we can do formation flying. We use them routinely to monitor activities in the tank. This is some work that we have done on autonomous vision-based flight control, where we're basically cueing off of a color-coded sphere and maintaining varied distance and separation from the sphere based on visual inputs. And human-robot interaction, which is a recurring theme. In this case, it's holding a tool board for the person who is standing in for an astronaut doing a particular servicing task. We had 2 programs quite recently that we hope will actually result in hardware developed in-house here at the University of Maryland and flown in space. Exospheres is a recent award from a combination of NASA and DARPA. So this vehicle is roughly ½ a meter on the side and about 50 kilograms total mass. Uses a phase change cold gas system for propulsion and has stereo cameras, so we plan to do vision guided autonomous flight control. And the idea behind this is this would emerge from the Kibo airlock in the Japanese segment of International Space Station and do inspection tasks outside. And then at the end of a 6 or 7 hour EVA, it would autonomously fly back and rendezvous and dock itself to a recharge station and then charge the batteries, fill up with the consumables, propellant, and be ready to go again. So this is a fun little project. And the idea behind it is that we actually are outfitting this with a standardized interface, both mechanically and electrically, for mission payload hardware. So one of the things we are looking at right now in my senior capstone design class, for example, is looking at a human mission to an asteroid. And they're actually baselining a unit like this with different scientific instruments that you could put in and go out and survey the asteroid and before the humans go out and do the critical sampling technologies. Another flight program we got quite recently is Dynaflex. This is part of the U.S. Air Force University Nanosat program. And the idea that we proposed was to build a small satellite. Again, this is about ½ a meter on the side, roughly 50 kilograms, and it would have a manipulator on board. The manipulator is a substantial fraction of the mass of the vehicle, and it is not your typical move at the speed of an hour-hand space manipulator. This is a typical manipulator that moves at the sort of speed you would see in the factory floor, and it's going to cause some pretty tremendous cross-coupling to the vehicle dynamics. And we're actually flying this as a flight experiment to understand how you would mitigate the perturbing effects of the manipulator reaction forces on attitude control for the spacecraft. And so this will be something we'll build up a prototype in the next 2 years, and then if we're down selected, take it to flight on an Air Force secondary launch. Sort of the flagship of the fleet in the Space Systems Lab is Ranger. This was a project that started in 1992 as an attempt to, I won't go through the long and incredibly tragic history of dexterous robotics in the space program, but in the early 90s, we basically come out of an experience with a program called Flight Telerobotic Service Unit by DME NASA. It's not my fault. And Flight Telerobotic Service are basically had cost escalation on the order of 600% and was closing in on $1 billion for total program cost by the time it was canceled, and which left the attitude around NASA, which still persists to this day at some level, that space robots cost $1 billion and it's going to take 20 years to develop. So we wanted to demonstrate that wasn't true. We proposed a very low cost, $20 million program to build and fly dexterous robots, originally on a free-flying vehicle, and then after some difficulties with that, we redesigned it to fly on the space shuttle. So this is our robotic servicing system. 2 8-degree freedom dexterous arms. These arms are faster and stronger and more precise than the human arm. They are intended to be human scale. We wanted the robot to be able to enter restricted volumes that astronauts and spacesuits can enter and do the same tasks. Our goal in designing this was a robot that could do anything an astronaut and a spacesuit could do. We didn't want to try to build an artificial human. A lot of people are building anthropomorphic robots, and that's not our thing. So we basically said, we're not going to try to replicate a human hand or anything close to the dexterity of a human hand. We're going to have an interchangeable end effector mechanism to change out end effectors. And so that has worked very, very well. These are different end effectors. The point to illustrate here is you don't just build a robot, you have to build an entire system. And that's the end effector suite. That's the task for the work on. These are Hubble electronics boxes from Hubble Space Telescope. And the setup for the remote controller. Coeur d'Alene was one of my first graduate students in this project, and this is a stereo video display with stereo graphic overlays to mitigate time delay. So it's really interesting, especially if you have time delay in the communications with what you have to do to get good performance out of a teleoperated system in the presence of time delay. So this actually, for many years, I could say, this is the only US built robot that has been certified for spaceflight. Recently, NASA flew Robonaut to the space station. So now I'm reduced to saying, this is the only US built robot that's certified to work in space, because they actually certified Robonaut to fly, but it was such a quick project trying to get it on the shuttle before the shuttle stops flying. They didn't certify it to be turned on. So the theory was get the hardware in space and then do the certification to turn it on later. So we could have turned this on had we gotten a ride to space. We didn't. It turns out that the Columbia accident eliminated any chance of getting a ride on the shuttle. But it's still a standard workhorse in the lab. We actually have thousands of hours on these arms now. I should point out that these arms work in the laboratory environment. They are certified for spaceflight, and they also work underwater. So, that's part of the paradigm in the lab, and it works very nicely. In 2004, after the Columbia accident, the NASA administrator went to NASA Goddard and said, I'm not going to allow more human missions to Hubble Space Telescope for servicing, but I'm going to give you some money, and you should look at the capability to do purely robotic servicing of Hubble Space Telescope. Now, we've been using Hubble as our standard target for servicing since the mid-'80s. So we're this is not a problem. What is a problem is getting people to believe that a university can deliver a robot that can fly in space and fix a $3 billion observatory. So they went to Canada, who builds the special purpose dexterous manipulator, which is known as SPITM, or no, they don't call it SPITM. They call it Dexter. And they basically arranged for that to be developed for flight, but the Canadian manipulator system is incapable of moving on the ground. Basically, you either do computer graphics or you don't test it at all until you get to work. And they came to us and said, could you modify your Ranger system to replicate the kinematics of the SPDM and do independent validation and verification of the tools and the tasks and the viewpoints, all the sorts of things we need to verify before we fly. And so I went through and said, okay, I've got to triple the length of these arms, I've got to double the length of positioning leg, I've got to build a body that basically violates everything we've ever learned about robotic servicing, that replicates this SPDM body, and I've got to come up with new end effectors that replace our interchangeable end effectors. The Canadian end effectors are roughly the size, shape, and dexterity of a trash can. So I'm being snotty, but it's true. Anyway, so it turns out, we said, sure, we'll do it. But we designed these Ranger arms to be very highly modular. One bolt can disassemble a module. The module has all the electronics located in it that controls the module. Electrical connections are automatically made when the module's made. We've actually had one robot arm disassemble the other robot arm. It's not good enough to put it back together yet. Anyhow, so the length of time we were down to do all that stuff I listed was 8 hours. And we were back in the water going again. Obviously, it took us a lot longer to build the pieces, but once we had the pieces, we could together and we're going. This is an axial instrument. This is the Hubble Space Telescope mock-up that the astronauts use to train on. This is roughly the size of a telephone booth. To insert this edge and the far edge at the top each have to be aligned within 50 thousandths of an inch. And we did that routinely with the robot. In fact, in the 4 months the program was in existence, we demonstrated every task that the astronauts had been planning to do on the SM-4 mission. And at the end of 4 months, when things were going great, Sean O'Keefe stepped down as NASA administrator. Mike Griffin was appointed as NASA administrator, and one of his first acts was to say, "There's no way robots can service Hubble Space Telescope. I'm canceling this program, and we're going to fly the shuttle there again." So they very successfully serviced it with humans again a year or so ago. And for those 4 months, we were doing really good. We try to do a lot with teaming. These are the same Ranger arms. This is a really cool facility if you ever get a chance to see it, down at the Naval Research Labs in southeastern DC. You're inside a large warehouse basically with 60, 70 foot ceilings. The entire thing's painted black. This is a large Fanuc arm with a payload of capability of 1,000 pounds or so. It's on a 2 degree of freedom XY plotter. There's another Fanuc arm on another 2 DOF Cartesian motion base at a higher level. So this is actually, the base of this robot is 15 feet off the ground. The base of this robot is 40 feet off the ground. And you can do relative maneuvering. So you have 6 or more, actually 8 degrees of freedom to the interface. We had the front end of Ranger and the 2 dexterous arms put on here as a servicing spacecraft. So we, on this arm, are the servicing spacecraft. This is the aft end of Hubble Space Telescope. On the other arm, as a target spacecraft, we can do relative motion and fly into grapple and do servicing with realistic dynamics and so forth. So that was an interesting project as well. You'd like to think that what you're doing is useful in the real world. So this is actually some work that a PhD student of mine named Brooke Sullivan did a few years back, where he looked at 2,400 spacecraft that had flown and with some kind of a problem during their lifetime. Of the on-orbit failures that were serviceable, where they didn't just blow up, he actually concluded about 20% of them were because the launch vehicle failed to deliver them to the right location. They needed to be grabbed and moved to the proper orbit. About 10% each just needed someone to look at it so you could figure out what was going on, or just needed a poke or a prod to fix one little thing that wasn't bad. But about 60% of it needed dexterous servicing, the kind of servicing we have demonstrated with our Ranger system and other robots. And this is just a notional view of the next generation version that's much smaller, much lighter weight. The interesting thing about it is the conclusion that Brooke came to is there's about $3 to $5 billion a year market for on-orbit servicing. And if you've been following this area, no reason you should have, but about a month ago, MDA, the Canadian company that builds the Canadian robots, announced that they were going to create a commercial entity to go to geostationary orbit and start servicing satellites. So clearly we're not the only people who believe there's a real market to this. The problem with Ranger, we were flying on the shuttle. The shuttle flies routinely with 2,000 to 3,000 pounds of lead for ballast to get the CG at the right place. So weight was not a criteria. So we basically made the thing, like a battleship. It's really massive. It's incredibly rich. One of the stories I love to tell, because we really wanted to fly that robotic Hubble servicing mission, and they said, no, we have to go with the Canadians. They're on this flight proven. Flight heritage is a big thing. So that April of 2005, the ground demonstrator for the Canadian arm was at Goddard, and we had our Ranger robots here doing the work that I was showing you. The MDA arm was in a clean room at NASA Goddard. You had to dress up in a full buddy suit to actually look at it, and only 2 people were allowed to touch it. They were both highly trained Canadian technicians. They were the only people who could actually move the robot, and because of the gravity limitations, they had big structure, gravity offset, and they could basically do about this, and that was pretty much it. And the same April, on Maryland Day, we had both arms in the water, and we had it set up where you could basically pick up things, move them around, or do peg and pull. And we had a line of 4-year-olds out the door driving the robot. And we're, now, whose robot is more robust here? Anyway, the problem is they're heavy. Each of the dexterous arms is about 180 pounds. If you're doing a servicing mission to GEO, you do care about weight. If the servicing spacecraft is about the same mass as the spacecraft you're servicing, then you need the same size and same cost launch vehicle to launch a servicer that you did originally to launch a spacecraft. It makes a lot more sense to just launch a new spacecraft. If the servicing system is small, then you can actually do a lot more. So this is a program we did for DARPA, where we said we think we can take the same capabilities as the Ranger dexterous arms and cut the mass by a factor of 8. And this is the prototype that we built of the elbow actuator. The elbow module on Ranger is 2 degrees of freedom, a roll and a pitch. This is the Ranger elbow module, and it's 46 pounds. This is the prototype lightweight elbow module that, when it's assembled into a complete arm, has all the capabilities that this arm does, and it's 4 pounds. So we actually cut the weight by more than a factor of 10. Coupled with our sort of modular philosophy, we said, what if we really pushed hard on the modularity? And we came up with the idea that we could actually come up, basically create as an outgrowth of the interchangeable end effector mechanism that we use all the time on Ranger, an androgynous interface mechanism, so we can plug anything in any orientation, and then come up with either single actuator, double actuators, whatever you want in terms of actuation, structural links of different sizes, different end effectors, different sensor nodes, force torque sensor, cameras, and then we have these nodes which either just do interconnects or carry power or carry specialized systems like propulsion system for free flight capability. So you can put them together however you want. This, for example, is a configuration that we optimized for doing a radial instrument replacement of Hubble Space Telescope. So these manipulators are actually used to react forces through EVA handrails. As long as we have 3, we actually have a very, very rigid connection of the system. And this larger arm with 2 dexterous end effectors give us the capability to do all of the EVA tasks required to release these instruments, and then enough stroke to pull them straight 8 feet out of the telescope for extraction, and then do the opposite for insertion. So we think the idea in the future is you shouldn't actually fly a robot. You're going to fly a robot toolkit, and then have the smarts to let the robot reconfigure itself to ideally fit whatever task you need to do. Since I'm talking about robotic systems, let me mention Samurai. This was a program that we started with NASA for sample collection in the deep sea. And you ask, well, why is NASA interested in sample collection? The program is called ASTEP, Astrobiology, Science and Technology for Exploring the Planets. And the idea was you were supposed to develop technology that would be useful for looking for life in the solar system, and then demonstrate it by doing cutting-edge science on Earth. So we teamed up with Woods Hole. At the time, no vehicle had ever been to the bottom of the Arctic Ocean. You can't send a tethered vehicle down because the ice pack will shift and cut your tether. So you basically go into the Arctic ice pack and an icebreaker, you cut a hole, you drop an autonomous underwater vehicle through it. It goes down to the bottom, it surveys the bottom, it comes back up, and it has to come back up in the same hole it went down. And then you can pick it up 36 hours later. So that wasn't nearly ambitious enough. So our theory was that in 2003, a German expedition had discovered evidence in the water column that there are hydrothermal vents on the bottom of the Arctic Ocean. You've seen these pictures of black smokers in the Pacific and the Atlantic with all of these colonies of chemical synthetic life forms around them that have no reliance on the sun whatsoever for energy. So the water in the Arctic Ocean has very limited interchange with the Atlantic and the Pacific. So you say that on average it takes 100,000 years to have complete changeover of the water in the Arctic Ocean. So as far as we were concerned, if there were hydrothermal vents and if there were life forms, it's the closest thing you can get on Earth to alien life in terms of connection with the rest of the world. And so we basically proposed to build a sampling system which started with the Dexterous robot. This is a 6-degree freedom robot. One of the things about the likely geological area for hydrothermal vents in the Arctic Ocean is the Mid-Valley Rift. The mid-ocean rift that where it occurs is 4.5 to 5 kilometers deep. It's the deepest rift zone on the planet. It's also the slowest spreading rift zone on the planet. So this arm had to be designed for 6,000 meters of seawater, which means that the external pressure on the arm is 8,000 pounds per square inch. So all of our systems had to work. We actually developed the arm. NASA ran out of money. The folks at Woods Hole went to the Arctic without the arm under NSF funding, which we didn't have at the time. And they did send a vehicle down to the bottom. They did not find hydrothermal vents. What they found is in the area they were looking at, there were evidently widespread fractures. So the hot water coming up off the magma seems to sort of come up diffusely from everywhere. And instead of having these localized colonies, the entire bottom of the Arctic Ocean is covered in this yellow microbial sponge. So we didn't get a chance to sample the sponge. I think they actually dragged it up with the vehicle. So they got papers in science out of it. We did get funding from NSF to finish the arm, which we're finishing up now. And we're hoping to have an opportunity to actually take it out to sea at some point in the future and try it out. Human system projects, I'm not going to talk a lot about this because you folks are interested in robots. We're interested in humans and robots together. We actually build our own, design and build our own spacesuits because if we want to do human EVA activity these days, that's the only way to do it. You can't get access to NASA equipment anymore. We do a lot of biomechanics instrumentation, which ties into robotics, as I'll show you in a bit. This is our MX2 suit. We've built 4 different suits so far, and we're working on the next generation of both of the lines of suits that we're doing now. This is a full pressure suit, by the way. It basically functions the same way any spacesuit does in space, although it's optimized for the underwater environment. What we use it for are human-robot interactions. We're really interested in how humans and robots interact, and I'm not just meaning how a human commands a robot, but how a human and a robot can work together in a single work cycle. So these are the things we'll. Excuse me, I'm getting over some kind of upper respiratory infection. And it still comes back to bite me occasionally. You saw the robot before. We've been very interested in how robots can help humans do. Use it up here later. How robots can help humans do servicing tasks. The big black box in front of the person in the suit is a battery pack for Hubble Space Telescope. It weighs about 450 pounds. Obviously, in space or in the water, it's neutral. It doesn't weigh anything, but it's massive. And so rather than have the human have to basically carry that, we have the robot here is providing restraint for the human in terms of the foot restraints that they're standing in. One robot arm is bringing the replacement battery pack to be put into basic bolts on the inside of this door. The other robot has opened the door and is holding the door open and is monitoring the human with the cameras looking over the top of the door. we have shown with this kind of interaction, well, here's actually the chart. We took the data we had, we looked at NASA trends and robot servicing. This was the first servicing mission to Hubble. We have the data for all the others. This is illustrative. So if you look at, on average, when the astronauts actually went up and did this servicing, they stayed outside each day for 6 hours and 15 minutes. That's the dotted red line. And so we then said, okay, of the tasks the astronauts did, let's divide it into tasks that are best done by astronauts and tasks that are best done by robots. And then let's further subdivide the robot tasks into tasks the robots should do before the astronauts get there, sort of preparation. Tasks the robots need to do to support the astronauts while they're there, or tasks the robot can do after the astronauts have gone back into the airlock and are eating dinner and sleeping. Think of it as cleaning up. And so that's the left, center, and right bars, the green and the yellow are the astronaut types. When we went through all of the activities, we basically just realized that the robotic system could save half of the time of the astronauts. And that was true on this one and things like SM-3B and SM-4. The servicing missions that have a lot of really, delicate, things that weren't really planned in the design phase to be done by astronauts, needed a lot of dexterity. We could save half the astronauts' time. If you look at EVAs that was more like plug-and-play box replacement, we could save 80% of the astronaut time. And so we thought that really shows the capabilities of these systems to help astronauts out. So if having a robotic system the astronaut works with helps, what if you move the robotics closer to the astronaut? What if you actually put additional robotic manipulators on the astronaut's backpack? Okay, extra set of arms. This has been known to my graduate students as the Doc Ock suit for Spider-Man fans. So the concept here is, maybe combining robotic and capabilities into the suit would be beneficial. This is not a functional arm, it's actually a rapid prototyping mock-up of the Samurai arm, but it's basically was serviceable for letting us figure out kinematics and reach envelopes, and can I take it from there, can I hand it back? We're interested not just in physical actions, but also in information. How do you get data bandwidth to and from the human? Right, you're in a suit, you're really in this very large, bulky, sort of like a 2-year-old that's bundled up to go outside in the snow. We've got very little capability. But we wanted to get a lot of information to the astronaut. We want to be able to command things. And so how you do that, this is actually a helmet-mounted display, and we have done this with both helmet and head-mounted displays. There's also a chest-mounted display here. He actually has a wrist-mounted display. So we've really been trying to, and also this camera is to let us see what he's seeing, and he can actually look at his own camera if he wants. And all this is voice control. This is a very recent test. We were doing some, I'll talk more about the thing in a bit, but we were doing some tests in the Arizona desert with our teamed university, Arizona State, looking at robotics supporting astronauts in geology tasks on the moon or Mars. And one of the things that, if you're on the moon, you have 14 days, 14 Earth days of nighttime. If you're there for a long period of time, we didn't think it was credible that you would just sit there and twiddle your thumbs for 14 days until the sun came back. And so we actually did some night traverses in the Arizona desert. This is Kelsey Young, who's a geology grad student at Arizona State, in one of our suits, and we were looking at lighting for geological exploration. And she also has a control panel, which you can see better in the picture, where she can interact with the computer in the backpack. She can interact with the rover that she's walking with, issue commands and so forth. And so we're looking at how all that works. In terms of commanding, this is some work we did for NASA Goddard. This is very similar to the remote manipulator system on space station or space shuttle. Obviously in 1G it only works in 2 dimensions orthogonal to gravity with these air-bearing pads. But rather than have to control this with a stick, we actually implemented a voice command system where you could start off by saying, 6 inches left, 4 inches forward, and then as you build up more capabilities, you can just say, grapple and dock, execute. We're really kind of interested in the long run of how to move a lot of robotic capabilities into the spacesuit. This is one of the first instances of that. Classic spacesuits do not have metacarpophalangeo joints, which means if you put your hand in a spacesuit glove and try to close your hand the way you normally do, it doesn't bend along your knuckles. There's no joint there because it would be it's a large joint and it has too much friction for a person to use it. So you grasp by bending at the proximal interphalangeals. And if you ever walk around the Johnson Space Center, and you can always tell who are the astronauts who have been who are going to go EVA on an upcoming mission, because literally for a year, everywhere they go, they carry tennis balls and they squeeze tennis balls, trying to build up these muscles, because that's not the way your hands are used to grasping. So we actually worked with ILC Dover, who makes all the spacesuits, and they made us a shuttle glove that does have an MCP joint. And as predicted, it's very difficult to move it. It takes 16 pounds of force. So if you try to do this manually, you get really fatigued. So we actually developed a robotic actuator that actuates the MCP joint, and then develops an adaptive nonlinear controller. This was actually Rob Sander in the Air Department who did that with. That would basically allow the glove to stay out of your way. So if you move your hand, it's sensed by the glove and it just actuates that joint for you. So it took the required hand force to move that joint from 16 pounds down to a maximum of 12 ounces. So it really gave you a degree of freedom in the glove that you never had before. So we think that was a pretty cool demonstration of capability. So our next goal is to go to the torso. Without going to a primer on how to design spacesuits, torsos where you have a neck ring, shoulder rings, and waist are difficult to design, difficult to build, and difficult to use. If you think about your shoulders, you have articulation on the clavicle and scapula, so that when you raise your hands, you don't just bend from the shoulder joint, the joints themselves move in relation to your vertebrae. So having a fixed shoulder joint, which you almost have to have on most suits, is very constraining. And actually, in the last few years, there have been a number of astronauts who had to have surgical reconstruction of the rotating column because of the constriction of the shoulder bearings. The helmet bearing is not a large, the helmet ring, you wouldn't think of it as a problem. It's not like you articulate that. But if you're walking on the surface of a planet, you need to be able to see your feet. And as the suit balloons out, you really need a way to sort of pull the helmet ring down so you can see your feet. And obviously, if I want to reach down, I need to bend at the waist. If you've ever seen films of astronauts in Apollo, they can't bend at the waist. So they either have long handles or tools, or they basically, if they need to pick something up, they fall over, pick it up, and then get back up again. So we came up with the concept of the morphing upper torso with the butt. So this is an early picture. It just has restraint lines. The idea is to actually put linear actuators in here. So you have as a rearatory suit, there's a ring on your back, which is the door that you use to get in and out. And we have parallel linkages to the helmet ring, to the two shoulder bearings, and to the waist ring. So each of these effectively make a Stewart platform, parallel manipulator. But the links don't run strictly to the ground plane, which would be the entry hatch. They run to each other. So it's 4 intercorrelated Stewart platforms that all have to be controlled together. Shane Jacobs, a year or so ago, got his PhD on the underlying theory of how you make 4 intercorrelated Stewart platforms work together. And so what this actually will allow us to do, if you think about getting into a spacesuit, you want it to be big when you get in, you want it to be exactly fitting you when you're operating it, we can do that. If you want to bend over, you want the suit to stay out of your way, we can do that. An extension of some of this work, I talked about articulation of the shoulder. A lot of people coming back from Iraq and Afghanistan have severe shoulder trauma because of IEDs. Sorry, that's a really bad mistake. Because of explosive devices, and they're standing up to peek over the armor. So they basically start off with no shoulder strength whatsoever. They can't do classic rehabilitation because the classic means of shoulder rehabilitation is resistive, and if you have no strength, you can't do it. And what they actually have to do now is a physical therapist will hold their arm and move it through all possible combinations, time and time again, 4 to 6 hours a day for weeks, to try to retrain the nervous system on what the signals are like as the arm moves. And then as they start to recover and build muscle, then you can go into resistance training. So what this is designed for, this is an exoskeletal system you wear. It has 3 degrees of freedom at the shoulder, but it also has degrees of freedom to track your shoulder motion as it articulates on the rest of your skeletal system. And it's strong enough that it can actually go through that phase of patterning and move the human's arm around, and then go into resistant mode. We're now looking at the medical people that are working with us on this. We did this for Georgetown Medical School. We're looking at it for things like stroke rehabilitation, where people have lost muscle control because of stroke and they need to retrain themselves. And we actually think of this as an extension of a completely powered spacesuit, so makes us happy too. This is just a little bit about our recent field tests. I spent spring break in the Arizona desert. This vehicle was designed and built by last year's senior design class in spacecraft design that I teach. It's a rover that's designed to assist astronauts in geological exploration. It has one of our early generation Ranger dexterous arms on it. We don't have wind effector, we're using scuba pointing on it. And because we wanted the actual flight version to be lightweight, it's a 3-wheel vehicle. I have a piece of advice. Any of you are building a mobility platform, even numbers of wheels are good. There's a reason you don't see a lot of 3-wheel vehicles out there. Anyhow, it's kind of interesting. The last couple of years we've been teaming with Arizona State because they are space scientists, and one of the things I'd like to do, a lot of, for our students in aerospace engineering, a lot of their career is going to be science-driven missions. And I thought it would be a good experience to have them do this interdisciplinary work, designing engineering hardware in response to the specifications and requirements of the science types. And I hoped it would be educational for the science students as well, to figure out how frustrated they're going to be when they graduate and have to deal with engineers. This is from last September. This is actually part of the NASA. NASA has a huge multi-week traverse field test in the northern Arizona desert every September called Desert Rats. And so we actually participated last year, and this is our spacesuit mock-up and Raven heading off across the desert. Now, actually, the NASA guys last year for their traverse started from this site and drove to SP Crater, which is this cove. This is a volcanic cove about 20 miles away. We went over there, but you know, we start small. We also did demonstrated the capability to command the robot to use a manipulator to pick up soil samples. And that's something we want to expand upon in terms of, instead of just having the, we were actually discussing this with the Arizona State folks. You know, at this point in time, the analogy, the best term for the robot in terms of assisting a scientist in a lunar traverse would be, it's a robotic mule, right? It carries a tool, it will provide lighting and things like that, but it doesn't do much smarts. What they basically, our goal is to evolve this, and these are the words of the head of the program in Arizona State, not mine. He said, your goal is to evolve it from a mule to a graduate student. You know, because you want to get the robot to the point where you can say, sample that rock, document this, pick that up, go look at that, tell me what you find, and then come back and be ready to help me when I need you. So that's kind of the paradigm we're working towards. This is our trip in March. One of the things we did was take some time to look at different ways to control the robot. Kelsey is wearing a glove we developed in the lab that actually has 3 different accelerometers. It has bin sensors on the fingers. And in this particular case, we're basically using wrist roll and hand grasp to command turning and speed of the rover. We actually have enough capability in this, we can do full arm pose. One of the things we use is for downstream is master slave teleoperation of the manipulator, where you can basically go through the digging motion and the arm will go through the digging motion with you. I just like this picture. This rover is, again, we tend to build things that are, one of the big problems that NASA had, they did some tests in 1999 and 2000 called ASRO, Astronaut Rover, Support Rover, and they said, this doesn't work, rovers are useless. And if you look at why they said that, it was basically because the rover they had traveled so slowly, the astronauts just walked away from it. Can't keep up. So we made sure that Raven was a robot that could keep up. This is where we spend our time, the Nutribuoyancy facility I talked about before. We have a lab in the Kim building. It's sort of off the wing that nobody ever goes to. So we've got our Advanced Robotics Development Lab, which is actually set up as a laboratory to build and deliver flight hardware. It's can be certified Class 100,000 Twain. We have a thermal chamber and a thermal vacuum chamber in here. Off of that, the 2 little back rooms, an electronics lab, and then receiving, inspection, secure storage, which is required for flight hardware. And then out in the parking lot of Nutribuoyancy, we had a program where we had built a full-scale mock-up of a lunar habitat and decided it was too fun to just trash after we were done with the program. So we brought in 15 tons of sand and built our little moonscape out there, which we call the moon yard. And we do a lot of our rover testing out there, as well as some of our suit testing. So that's kind of a brief overview of what we do. I'll be happy to take any questions, or if any of you are in the neighborhood, stop by, I'll be happy to share it around. Any questions?
So, I mean, which direction now is space robotics is headed? I mean, according to the latest information from NASA.
Nobody knows. Basically, the space program is in a state of catatonic helplessness in response to political forces. The administration has a vision of significant support for advanced technology and developing technology to go beyond where we are now in space. Powerful elements in the Senate have a vision of funneling the maximum amount of money possible to their centers in their home state to do things that are not particularly useful, but will be big money to their home state. So there's a mandated program now that's been $3 billion a year, and what people are now terming the Senate launch system. Since the senators are not only demanding that the NASA build this launch system, but it's telling them how big it has to be, what kind of engines it has to use, what kind of staging it has to, so like these, and I will point out there are no rocket scientists in Congress, but they're telling NASA exactly how they are supposed to design this vehicle. And if you look at the continuing resolution, the Office of the Chief Technologist was zeroed out of the continuing resolution, although NASA's pulling some shenanigans to keep some funding going and just start a technology program. So the short answer is nobody has any idea whatsoever. I'm hopeful that somehow or the other people will be convinced to do the intelligent thing and support future technology. But it's cumbersome. I mean, why should I think that?
Yes, you mentioned that while wearing spacesuits, astronauts end up with muscle degeneration and such things. I was wondering how long these spacewalks are, how long they should be to cause such damage.
It's, excuse me. A typical spacewalk is 6 hours. And they are fatiguing. They're not in general damaging. If you go back to the Apollo program with the lunar missions, to make sure that they had good contact with their gloves and the tips of the gloves, so they had good tactile feedback. The astronauts would shorten the length of their arms. So there's actually quite a bit of force driving their fingertips into the glove tips. And several of the Apollo astronauts basically bruised their fingertips to the point that all of their fingernails fell off some period of time after the mission because of that. But you know, the problem with the rotator cuff is actually not a problem of using the suit, it's a problem of getting in the suit. Because if you think about it, you know, the side bearings that your shoulders need to be in are more or less vertical. But in our suits, you come up from underneath, and you have to get your arms through these bearings, and then turn your arms in the direction your skeleton does not allow them to turn, while your torso and head are coming up to get your head out of the neck ring. And so the problem is, it's very difficult to get in and out of the suits, and that's what's causing most of the rotator cuff problems.
Most of the manipulators, when they operate, then they're controlled in the task.
Yes, all of the manipulators are typically controlled in end effector coordinates in resolved rate mode. Actually, Ranger has a number of different coordinate frames you can specify. So that when you change end effectors, there's actually a new data set that's loaded so that you're in the tip frame of the end effector regardless of the end effector. So if you come up with a longer end effector, you're in that tip frame. We also can go in base frame. We can also specify a task frame and operating task frame.
So when you say, so basically the manipulator that you're teleoperating and the person that said who's moving it, they are different manipulators, right? You're probably using a joystick to device to teleoperate a complex manipulator.
We've looked at a lot of different devices, but the bottom, you know, everyday version of 2 3-degree freedom hand controllers. So one controls the rotation rates of the tool point, and the other controls the translation rates of the tool point.
And the joint, for example, the constraints on the slave manipulator, if there's some joint limits and stuff like that, those are automatically maintained and stuff?
Yeah, actually, it's quite interesting because these manipulators are all redundant manipulators, 7 and 8 degrees of freedom. And so our control algorithm, usually you can change it, but the typical operating mode is to take the 7th degree of freedom and use that to control the shoulder, elbow, wrist plane angle. And so you can hold a tip position and do that. And so we drive the STW angle to maximize distance to the nearest singularity. So as you go through a maneuver, you actually see the arm doing some really weird motions and the wrist reconfiguring itself, which we know what it's doing, and it's good. It keeps us away from singularities. It makes it easier to use the arms. The funny thing is we had some astronauts in running the arms, and the first time it went through one of these reconfigurations, the guy went like that. And he said, "It's broken." I said, "No, it's what it's supposed to do." And they have this mindset that nothing moves unless I tell it to move, right? So they really did not like this moment. So I said, "Okay, I'll turn it off. If you want to change that angle, flip that little thumb controller on your joystick, and you can change the angle manually. But you got to keep it out of the singularity now because it's not doing it for you anymore." We've learned a lot, particularly with the Ranger arms that are 8 degrees of freedom, and then we have 2 more degrees of freedom in the end effector. And you wouldn't think it, but we actually find there's one set of controls where it's an 8 degree of freedom with a 2 degree of freedom manipulator, and then we can mode switch and make a 7 degree of freedom manipulator with 3 degrees of freedom on the end effector. And it really makes a difference. There are some tasks that work better one way, and some tasks that work better the other way.
What's it like, the corrosive, think about corrosion, you have to think about, I know a little bit about, underwater, how you have to build something so you can pull it out and it doesn't rust the next day. But nothing about, vacuum. For instance, if you take a cheap transistor radio and slow enough, let the air equalize, and then bring it back in, is it going to work, or is it similar, the level of worries about rust and water being so corrosive?
Paperwork aside, I will tell you it is much harder designing an underwater robot than it is to design a space robot. We built the Ranger arms as underwater robots. The flight arms were identical to the underwater arms, except we left out the seals, right? Because we wanted them to go to vacuum. The electronics works fine in vacuum. We designed the arms so the thermal paths were correct, so the arm wouldn't overheat in vacuum. When if you compare the difficulty of a flight manipulator, space flight manipulator, to a 6,000 meter deep submergence manipulator, there's it's orders of magnitude difference in complication. Much easier to build a flight manipulator. Now I did say paperwork aside, because you have to basically have 10 times the mass of the arm and paperwork to get a flight system.
I think we should
One more?
finish. Yeah, go.
Okay, I'm just interested. Do you see room for immediately for adding perception to add their cameras and automate parts of the jobs with things like scoring in for visual feedback?
Oh, absolutely. One of the things that's really important is adding sensors to the robot of all kinds. Tactile sensors, force torque sensors. These arms are capable of compliance control, but one of the big problems we have is because of the problem of waterproofing a 6-axis force torque sensor at the wrist, it really destroys the accuracy we want to see for compliance control. We're doing a lot of work in visual-based servoing now, and it's would like to try to make it where you don't have to have cameras all over the place, but to some extent, is necessary. We do a lot of work with humans being next to a robot, and the robot is capable of doing some serious damage to you. Now, we have a control system for these robots that we had to develop to certify to NASA flight standards, where there's 3 levels of redundancy. You have to, it's basically 3 fault tolerant before anything happens, and it saves itself in 30 milliseconds before it starts to run away. So because of those safety systems, we feel confident in having a person close to the robot in a controlled situation. One of the things that people have talked about a lot and would be very beneficial is some kind of sensor skin that will let you detect if you're about to hit something you don't know and stop the arm that way. Really kind of hard. People have done it on the ground with capacitive sensors and with photoreflective infrared. Really hard to do that. You can't do it underwater with capacitive because it doesn't work. You can't do it in space with the reflective infrared because the sun just blinds everything. So it's not that easy a problem, but more sensors of all different kinds, more perception to the robot would be very, very beneficial.
All right, I think what I'm going to recommend that we end your talk to the people who can head out, and the people who still want to ask questions, hang around, and I'm sure that they will.
Okay. Thank you.